Okay, so my project was quantifying the accuracy of high redshift galaxy classification in the extended Groth strip field. So, for an overview of my project, basically the galaxy classifications in EGS need to be reviewed to see if a flagged source is actually high redshift. Um, so, often we'll see problems with the IRAC residuals, which classifiers will report to us when they classify. So, as either a good IRAC or there's a specific issue with an IRAC. Um, so, my project is to look at the statistical qualities of sources with good versus bad IRAC data in the residual plots in order to see what causes these bad classifications. So on the left is an example of what an EGS classification plot would look like. So what I'm specifically looking at is at the bottom right here, these residual plots. So these are what I'm concerned with, and this is what the rest of my project is going to be talking about. So I have 5 steps in this project. So my first step was to determine the size in pixels of the residual stamps, which was, I was told is 10 by 10 arc seconds, and you can see that in this image here that's 10 by 10 arc seconds. So what I had to do was use AstroPy to convert from arc seconds to pixels. And so essentially what I ended up finding is my stamps need to be about 16 by 16 pixels. So then my second step is to cut out residual stamps at a list of marked positions, which I ended up doing in MATLAB, and I'll show you in a minute. My third step is to separate good and bad IRAC sources. That way I can go back later and compare the two and see what their differences are. Step 4 is to observe the statistical qualities by measuring a few different pieces of statistics. The ones that I chose are mean, central mean, which is the mean brightness in just the center of the image, standard deviation, which I also decided to do 2 of those, and I'll explain the second one in a few minutes as well, correlation coefficient, and variance. And then my step 5 is after I have all those statistics, I can look for common patterns in the bad IRAC sources compared to the good ones. So I can basically compare what those results look like and what the commonalities are in what makes an IRAC source classified as bad. So the first thing I did coding wise was to create this stamper function. So the first step in this whole process is to cut out stamps of the flagged galaxies from the original image. So the stamper function that I wrote loops through a list of galaxies in a catalog that I was given and cuts out that 16 by 16 pixel stamp centered around the coordinates and saves it along with the galaxy identification number. The function, I decided to skip galaxies at redshift z is z less than 5 because we don't have classifications for those, and we're specifically looking for high redshift galaxies anyway. And it saves those stamps into their corresponding good or bad IRAC folder so that I can split them up and look at them separately when I get to MATLAB. So, like I said, I did this in Python. So, essentially, what it does is I read in this original image file, which is in a FITS format, which is up here at the top, and it has all these galaxies in it. And then I also have a catalog that has a list of flagged galaxies that includes their galaxy ID number, the position in RA and DEC, the whether or not the IRAC data was classified as good or bad, and also a few other pieces of information that weren't as relevant. But one thing that I did have to do with this function is that since I was given the coordinates in RA and DEC, I had to convert those to pixels, which similarly I ended up using AstroPy, which was really helpful to me. So once I get those, then I can cut out the stamp, and this is what those example stamps would look like. This is a few of the ones that I cut out. So then once I have those stamps, then I decided to move to MATLAB for the statistics because personally I prefer MATLAB when it comes to statistics and things like that. So what I ended up seeing is that after I transferred the stamps to MATLAB, some of the statistical values were not maintaining accuracy due to very small numbers for their brightness values, which was a problem. So to fix this, what I did was I wrote a function to use vector mapping that could change the size of the values of the images without affecting the scaling or proportions of the brightness. So essentially, what that means is I changed the range of the image, but without affecting the actual proportions relative to each other or the scaling and things like that. So um, it's given by I put the equation on the slide. Basically, we have the output vector image, the input vector image, and then I give the function the range of the original and also the range that I want to convert it to. And then the equation does the work for me as it runs through each element of the vector. So I also did test this to be sure that there's no loss of accuracy. I tested it by converting it back to the original form to make sure that converting it wasn't causing an issue with brightness, and that did check out. So there was no loss of accuracy there. So some of the stats functions I chose to use were the mean, which is the average brightness of the image. I used one for the whole image and also one to show the brightness of just the center of the image. I also chose to use correlation coefficient, which is the strength of relationship between two variables. So in my case, it would represent how correlated the image pixels are to each other. So basically, the correlation in reference to each of the other pixels. Standard deviation is how dispersed the brightness is with respect to the mean brightness. But I also used another kind of standard deviation, which is vector weighted standard deviation, which basically means that it's the same as standard deviation, but it's normalized with the number of pixels in the image vector. So it's pretty similar to standard deviation, just a little bit different. And then my last one was variance, which is also really similar to standard deviation. It's almost mathematically, it's very mathematically related. So it should appear very similar, but it's how far the brightness values are spread out of range with respect to the mean. So then here are the scatter plots that I ended up coming up with. So you can see on the left, I have the brightness of the center, I have the brightness of the whole image, and I have the correlation coefficient. So if you kind of look at all of these scatter plots, of course, the good IRAC sources, there's just more of them. So that's why there's more sources. But you can kind of see how they tend to follow the same pattern. So you can tell the trend isn't very different for these particular values. But once you look over to standard deviation, both kinds, and also the variance, you start to see an interesting trend, which is that the good IRAC sources are very spread out, and the bad IRAC sources are very clustered towards the bottom. So essentially, what that means is that bad IRAC sources tend to have a low standard deviation or a low variance, which is actually the opposite of what I expected to come up with, because I thought maybe the algorithm would mess up when the standard deviation is too high and there's too bright of a pixel or something like that. But that's actually the opposite of what I found. So this is definitely something to look into for the future on the project. So some future steps, how to continue. The first thing is to determine what good IRAC sources would be lost if we choose to exclude sources with low standard deviation. So if we look back at these, obviously if we were to exclude all of these bad IRAC sources just based on low standard deviation, we would lose some of these good IRAC sources. So we need to determine which of those would be lost. Also, check to see if the statistics are related to the source's position in the full image. So, looking at edge galaxies versus center galaxies and seeing if that could potentially change how the statistics look and how the relationships look. And then also to create histograms to look at some specific sources and take a look at the standard deviation and variance trends on the smaller scale, and maybe potentially figure out what exactly is going on in those scatter plots and why the bad IRAC sources tend to have low standard deviation, which is the opposite of what we thought would happen. So that is the future of the project.